So let's start off with what type of graph do we use. So this is a really good little summary to go in the smaller side of the summary book. So a really good summary to say, all right, if I've got categorical numerical data, it's going to go in one of these three types of graphs or tables. Now, if I actually have numerical data, that is, as you can see here, one of those 1, 2, 3, 4, 5 graphs or tables can be utilized to display numerical univariate data. So below you can see here, you've got a frequency table. So frequency tables are really interesting because they're just the raw data shown to you in the easiest way they can. So raw data is data that has been manipulated, it's just obtained, and it's just what they had on their sheet. You're generally going to obtain your data for something like this in a frequency table. So it's the easiest and most simple way of displaying it. Usually you don't want it displayed in a frequency table. The only way a frequency table can get a little bit more complex is if you put a percentage in it. So a percentage frequency table is essentially when you get the whole cohort and you find out what percentage each one was, and it should total out to 100%. Now you can add this as an extra column, or you can just make it separate like this one here. The most common way of displaying categorical univariate data is through a bar chart. Now, a bar chart is distinctly different to a histogram, and we will discuss that when we get to our histograms. But it's really important to understand that categorical data has this sort of broken up approach. Because the categories, order or not, are separate, they don't sort of follow along by numbers. We need to break them apart. We need to have gaps between our bars. So in a bar chart, there is a gap between each bar. Also in a bar chart, we usually try and keep it as one color. So we usually try and keep each of the bars the same color, they're the same width, and they're the same distance apart from each other. The only difference is their height, which is obviously their frequency, because on the y-axis you've got your frequency, and on the x-axis you've got your categories, so your type of pet, or etc., or whatever it is. As you can see here, pets at home, and you go, all right, I've got cats, dogs, birds, fish, etc., and you then do your frequency on your y-axis. So categorical data is also really interesting because it can be described in a really sort of succinct and straightforward way. So there's a template that I want you to use in your summary book as to how you're going to answer all categorical numerical data questions where they want you to explain it. They want you to write a paragraph. They want you to say, hey, what actually does that graph show you? What is that graph telling you about what's going on? So you must essentially summarize the context of the data. That's always the first thing that I think you should do. You should always summarize what is going on in your data. So give some context. What is it? What are we actually measuring? Or what are we counting? What are we taking the frequency of? What's going on? So obviously you won't be measuring and counting to use a categorical, but nonetheless, you're saying, all right, I'm getting the frequency of the number of the type of pets people have in my class. You want to identify the mode, so usually what's the most dominant category, and then quote its frequency, and then quote other frequencies of interest. So let's have a look at this question here. I want you to comment on the data shown in the frequency table below. So if you want to have a go at this, please feel free. I'll pause it here, or you can pause it here. So pause here and take a good 30 seconds or so, maybe a little bit more, maybe like a minute, and write out an answer that gives all 3 or 4 of those points: context, what is the most dominant category, what is its frequency, what is some other points of interest. So here we've got, all right, so 3, 2, 1, pause. All right, hopefully you're back. So here we've got 3 climates: hot, mild, cold. We've given the frequency, we've given the percentage frequency. So we'll start off with, this is what our answer looks like, but how do we break this down? Well, first of all, we had context. The climate types of 23 countries were classified as being hot, mild, or cold. So we've given context. There were 23 countries that were surveyed in this sense. We weren't given the context that they were in the question. You weren't given the context that these were countries, so if you didn't mention countries, that's okay. But obviously in this question, we were talking about countries. And we wanted to classify them as being hot, mild, or cold, mild, hot, whichever way you want to talk about it. It doesn't really matter. Nonetheless, that's a good way of sort of looking at it. Then we say the majority of countries, 60.8%, were found to have a mild climate. Now, really important, Percentage frequency dominates standard frequency. So please use percentage frequency if it is available. If it is not available, you can use your common frequency, but I always suggest using percentage frequency over common frequency because it's already been manipulated. It's a better piece of data. It's a better piece of information. We like it more. It gives and provides more information. So therefore, I always say, you know what, if it's there, utilize it. And then we've got our other pieces of information. So note other frequencies. So of the remaining countries, 26.1% were found to have a hot climate, while 13% were found to have a cold climate. So it's just commented on the other frequencies. Now, this table might have been much larger. There might have been, 8 categories or something. If it's much larger, you don't need to comment on every single one, just ones of note. You could say the least common climate was cold with 13%, or the next most common climate was mild, or hot, sorry, with 26.1%. So you just give what is the next, what is the least, or just something that's interesting. You don't want to say every single thing. In this here, you can because there's not a lot of information, but you don't want to go out there and just write every single thing down on the page. So then we move into numerical. So numerical, also really interesting. You can also display numerical data in a frequency table. Again, this is your last resort. You don't really want to be doing this. So it's sort of the last resort as such. And you can sort of put it into a frequency table. You can also sort of range it. So in this case here, you can use ranges. Think of this as like intervals. You're also welcome to utilize this with tables. But again, last resort, we'd rather use like a dot plot. So if we look at this here, we go, all right, dot plots used for discrete numerical data. Only the x-axis is used, so we don't have a y-axis. And the number of dots represents the frequency. So essentially, we have pieces of information that are on 1, 2, 3, 4, 5. Sorry, that's sort of been squished down. Didn't really hold its position well. But as you can see here, we have 4 on 1, we have 2 on 2, we have 1 on 3, etc. So what we're looking at with the dot plot is just, we're looking at sort of how many pieces of information are each one. We can then sort of find a mean, median, or a mode, etc. This would really be used for this numerical discrete rather than numerical continuous. Numerical continuous is probably not all that useful on this one here. You can find the mean. You can do that by counting the dots and then finding the middle value. So if I go here, I've already got it up on my page, but if I go 1, 2, 3, 4 in our first one, I've got 2 in my second one, that's 6. I've got 7, I've got 8, 9, I've got 10, 11. Well, my middle point is going to be my 6th point because there's 5 on either side. 1, 2, 3, 4, 5, and then 6, and pardon me, and then 7, 8, 9, 10, 11. So there's my 2 points of 10. So having my 2 points of 10, I'm therefore going to have my middle point being 6. As you can see here, I've got 4, and then if I'm counting down, I can say 1 and then 2. That's my 6th point. If I'm counting up, you're welcome to do the top one. Doesn't really matter. Both going to end up being 2. You've got your median value. And then you got your stem and leaf plots. Now, stem and leaf plots can be utilized for continuous. Once again, probably still not all that useful, but you can use continuous data on it. Probably the more useful way, we'll talk about it in a bit, but it's more useful here to do numerical discrete again. Now, you've got a stem. So essentially here we're saying that our stem represents 40, so 4, and then whatever goes behind it is the 1. So this example here would be 41. So your stem is the first digit, your leaf is the last digits. Same with the stem, it can be more than 1. So example, as you can see, it's like 40 and then 1. You always need to include a key here because in this case here, what if the 4 was representing 400 and then the 1 was representing the 10s? So it could be 410. Really important that you do that because in most cases, if you don't have a legend, you cannot utilize a stem and leaf plot, and your answer will be wrong if you draw a stem and leaf plot but don't give a legend or a key. As you can see here, you got your stem 1, 2, 3, 4, 5, 6, and you've been told in your key that if it's 1 and then 0, it's 10. So if it's 2 and then 0, it's 20. If it's 3 and then 5, it's 35, something like that. So you can see here in your stem and leaf plot, you've got a whole bunch of values. They've been ordered. And as you can see, this answer is 10. But if I said, oh, what if this was 100? Well, then I'd have to make this 100. So it's really important that you know how to utilize that, you know how to apply that distinct methodology of utilizing a stem and leaf plot. It is a little bit difficult. So really important, a leaf plot has to be ordered, and you can split a stem and leaf plot. Now what I mean by that is, so let's just use 2 here for example. So you can see our 2 on our screen. We have a bit of information, we have 4. Now what if I wanted to break that down and say, all right, I want two categories. Well then I'd go, 1, 2, and then 2 again. Now the first 2 category, you go 0 to 4. The second 2 category, you go 5 to 9. Now you're welcome to do that. If you do that, you need to do it for all of them. So for example, in our 4 one, as much as there's only 3 things there, you'd have to do 2 4s. You go 4 and you'd have your 2 4s next to that. You go 4 again and you do your 7. Same as 6, you do 6 and you go 0, 1, and then you do another 6 below it and you do the 9. So you are welcome to do that when you have lots of information. Breaking down a stem and leaf plot into doubles is really, really useful, but only do it if it's, you've got like 6 or 7 pieces of information in each one. I think if it's less than that, like this one here, it works as is. I think once you get to like 6, 7, 8, then it's useful breaking it down. But before that, it's not that useful. I wouldn't bother doing it. It's not all that. It's not the best thing you can do. And it's not called a stem and leaf ploys. Sorry, it's a plot. Now, histograms. Now, this is where we talk more about a numerical discrete. And the best way to talk about this is usually putting things into categories. Not categories, intervals. Sorry, I shouldn't say categories, I say intervals. Putting things into intervals. Now, the example I put on the screen doesn't have intervals. Once it pops up. No, it does have intervals, sorry. I did change this. The example we used to have didn't have intervals, and I was like, it annoyed me. So I've obviously gone and changed it. I did forget that I changed it. Intervals. So intervals are really, really useful because then all your continuous data, you're sort of sub-categorizing it in a sense, but it's still categorical data and using the raw data. So in this graph, you cannot find your mean or your mode. It's not that useful. You can find a median or a mode in terms of your intervals, but that's not useful. You get your raw data out and that's when you find your mean, your median, your mode. What you look at here, if you're able to describe this, is you look more at the shape. You look at the spread, you look at the center. So you say, all right, our central spot is between 5 and 9. So you don't talk about the exact median or the exact mean. You talk about your center spot. And then you talk about outliers. You might have a bit of outlier information. Like you might have a really big peak somewhere and it's not that useful. You talk about that as an outlier. So that's where histograms become more common for numerical continuous because then you sort of interval it. You put that information into intervals and you get the relevant information out. Now, numerical continuous data is most useful when it's bivariate. We'll talk about that a little bit later on, but that's because sort of our bivariate data just provides a little bit more oomph, if that makes sense. You get a little bit more ability to manipulate, you get a little bit more ability to work with it, and a little bit more ability to sort of just display it differently. And that ability really, really shows when you have continuous data. And continuous data is far more useful when it's bivariate. When it's univariate, it's not as useful. So this is where univariate data gets really tough. So univariate data as a whole is not all that difficult. This is where it gets quite difficult, and this is the point in this session, which if you haven't really been paying attention, that is fine. You should pay attention right now. This is where things get a little bit difficult. So sometimes we have a data range and it's too big. The most common example of this is if you look at the populations of the world. You look at somewhere like Samoa, and I think Samoa is somewhere around, 9,000, 10,000 people. Even like Vatican City. Vatican City, don't ask me how that is a country, but nonetheless, Vatican City is something like 300 people. It's really, really small. Same with somewhere like Samoa. Samoa has something like 9,000 or 10,000 people in it. So that's really small. But then you compare it with somewhere like China or India, which have over 1 billion people. You put them on the same histogram, and it just doesn't work. You're too far apart. You cannot work with that. Your histogram is going to take up more than one page because you're just spreading it out. Unless you do really big categories, and then that sort of skews it. It's not right. You're sort of manipulating it incorrectly. So in these cases, we use what is called a log scale histogram. And you might say, what the heck is that? A log scale works like this. So a normal scale goes, 0 to 10, 10 to 20, 20 to 30, 30 to 40. So you have 10 in between them. That's how a normal one works. So if I've got 10 in between them, I'm counting up. So we use pluses and minuses on a normal scale. We plus this much or we minus this much. A log scale works by multiplication or division. So 1 to 10, multiply by 10. 10 to 20, 10 to 100, we're multiplying by another 10. If I go 100 to 1,000, I'm multiplying by another 10. So a log scale puts things in categories of 1 to 10, 10 to 100, 100 to 1,000, 1,000 to 10,000. So the intervals are all different sizes. However, they are the same width apart. You're not making the intervals different widths apart. You're keeping them the same width apart, but what is in the interval is very distinctly different. The first interval is made up of 10 numbers. The next interval is made up of 90 numbers. The next interval is made up of 900. The next interval is made up of 9,000, etc. And so therefore, a log scale gives these numbers. So there are a few properties I want you to understand before I sort of describe that. If the raw piece of data is greater than 1, its log value is greater than 0. If a number is greater than 0, so the raw piece of data, so it's between 0 and it's between 1. So it's like 0.5 is the piece of data that you got. Its log value is actually negative. So you're going to get a negative log value. So your log value will be negative. Now you do this all on your calculator. If the number is 0, so they actually didn't have anything, so you're measuring and there was nothing, it's undefined, you're not going to be able to log that, don't worry. And for some reason you are measuring something that goes into negatives, maybe temperature. If the temperature is in its negatives, you actually cannot utilize logs. So there's no way of logging a negative number, it doesn't work. So therefore what we're saying is that if you're measuring temperatures and they're really, really far apart and you wanted to use log scales, but then you get a negative temperature, well, you're not going to actually be able to plot that piece of information on the log scale. So when displaying logs on an axis, we use their order of magnitude. So 10 to the 2 becomes 2, therefore we must label the axis as log variable. Now, this is what I mean by this. So essentially, and again, I didn't fix this one, I should have fixed this one, this histogram is wrong as well. These are intervals. Think of this interval as 0 to 1. So the first one here, as you can see on the screen, this is 0 to 1. So if I am between a log of 0 to 1, where am I? So remember we discussed on our last page that if the raw piece of data is greater than 1, then our log is greater than 0. Well, if I'm between 0 and 1, that means my raw data is between 1 and 10. So this is between 0 and 1 on a log. It's between 1 and 10 in my raw data. If I'm between, next category, we'll say this is between 1 and 2. So we'll say, all right, this is between 1 and 2. Now, being between 1 and 2, I say that my log is between 10 and 100. So my raw data is between 10 and 100, but I'm saying it's between a log of 1 and 2. Next one, I say, all right, it's between 2 and 3. Again, this got squished down. I do apologize for that. I don't know why a lot of the graphs it's because I changed the shape of the slides to fit the full screen and they got manipulated down. To apologize. I should have edited that out. But let's just say the next one's between 2 and 3. So our next one here is between 2 and 3. Being between 2 and 3, we say that is between 100 and 1,000. So any piece of information measured is between 1 and 1,000. And that's why we call this log and then whatever our variable is. So if we're talking about population, we'd say log bracket population. And as you can see here, this is what our log guide means. So your log is the value up here. It's this value that the 10 is to the power of. So a log of 2 is essentially 10 to the 2, and it is 100. A log of 3 is essentially 10 to the 3. 10 to the power of 3. 10 to the power of 3 is 1,000. A log of -1 is equal to 0.1. So if my interval is between a log value of -1 to 0, I'm between 0.1 and 1. Now, if I'm between a log value of 0 and 1, I'm between 1 and 10. So that is your guide. Now, how do I actually calculate logs? Like, what if I've got a value of, 245? Well, I've got a value of 245. Oh, maybe we'll use something. Shall I use something else? What about if I say I have a value of 150? I have a value of 150. Now, you might say to me, I think that is going to be 1.5. 1.5. I've got a log of, no, wait, that's 15. I'm going to say 150, sorry. I've got a log of 150. So you might say to me, being a log of 150, you could figure out where it's going to be, and you could say, it's going to be close to 2. Well, that's probably right. I was trying to think of probably a better way of saying it is, what if I thought of a log of, we'll go back here. I'm looking at a raw piece of data, and my raw piece of data is 5.5. So 5.5 is smack bang in the middle of 1 and 10, because there are 9 numbers between 1 and 10. The middle is 4.5, so I add 4.5 to 1, I get 5.5. So I'm at 5.5. My raw piece of data is 5.5. My raw piece of data being 5.5, being smack bang in the middle of 1 and 10, I would assume it would be smack bang in the middle of 0 and 1. What you'll find is it's actually not, because log scales go up very differently. They don't go up uniformly because of that multiplication, and therefore your actual log value might be more like, a 0.4 or a 0.6. It's not going to be 0.5. It's not going to be smack bang in the middle, even though the raw data is smack bang in the middle. Now, always use your calculator to calculate your log value. So if I want to find a log value, I've been given the raw data, and I say, all right, I've been given 150 as my raw data. I go log 10 of 150. Now, this will be in your calculator. You'll be able to find this in your calculator. There is a log in your keyboards for your Casio class pad, or if you're on your TN Inspire, there's actually just like a shift shortcut to one of the buttons, and you find that you'll get your log 10, and then it will give you brackets, and you just have to put the number in the brackets and press enter, and you get your answer. So as you can see here, your log 10 of 150 is 2.1, which if I go back, it makes sense. It's between 2 and 3. And also really important here is to identify how a log scale is working. 150 is only 50 of the 900. There's 900 raw pieces of data between 100 and 1000, and I'm only 50 in. I'd assume that I'm actually less than 10% in. So 10% of 900 is 90. So if I was going up uniformly, my log of 190 would be 2.1. And therefore my log of 150 would be less than 2.1. But my log of 150 is more than 2.1. That's because logs go up differently. They go up on sort of an exponential sort of way. They go up non-uniformly, and therefore your log values do not exactly match the exact position that your value is. Really important to understand. That's why you need to calculate it every time. So put it in the calculator. Now, what if I have a log number and I want to find what my actual value was? Well, if I'm given a log number, I just go 10 to the power of the log. So if I was given a log of 1.683, I go 10 by 1.683. And being a log of 1.683, I assume it's between 10 and 100, because I've got this scale here. Well, it's 1.683, and it needs to be between these two pieces of raw data. It is. It's 48. It's perfect. It's perfectly been pulled out, and it's in between our 10 and our 100 because it's 48. Always use your calculator. This is a really good example to have in your summary book. Same with this one back here, having these two in your summary book next to each other, with then an example of a question such as this. This is a VCAR 2016 question. It was really poorly answered, like extremely poorly answered. I want you all to have a go at it. I know this is your first time seeing logs, so if you do struggle with it, that is okay. This is your first time seeing logs. I don't expect you all to be acing this straight off the bat, but I do want you to have a go at it. So as you can see here, we've got a histogram below that shows the distribution of number of billionaires per million people for the same 53 countries as question 6. Don't worry about the countries, it doesn't really matter. Based on this histogram, the number of countries with one or more billionaires per million people is. So this is the number of billionaires per million, and it's counted in each country. So they counted how many billionaires per million people there were in each country. And then for each country, they were like, all right, so there is 5 millionaires per person. All right, we'll do a log scale and we put it in. So it says here, the number of countries with one or more billionaires per million people is. So how many of these countries, how many of these people in this graph here display more than one billionaire per million people? So more than one. But remember, this is on a log scale. Really important. So, have a go at this question. I will give you, I'll give you some time. Again, pause it. 3, 2, 1. Pause. And hopefully you're back. Now, if you're back and you're confused, I will explain a little bit more of it, then you'll be welcome to pause it again and have another go at it. But if not, we'll jump into it. So as you can see here, we have a log scale, and we want to know the raw number of people, or the raw frequency of more than one. So what is a log of 1? Well, the first thing I would do is I'd go to my summary book. So I'd go to my summary book and I'd go here. So hoping this clicks in. I'd go to here in my summary book and I'd go, all right, what is 1? Well, 1 in my summary book is 10 to the 0, which is a log number of 0. So if it's a log number of 0, I need to go to here. And a log number of 0 is here. I draw a line up here just to cut off everything to the left. I don't care about anything to the left. I only want the stuff that is on this right side here. So being on this right side, I look at the frequencies and I go, all right, well, between 0 and 1 means there is 1 to 10. So the number of billionaires per million people is somewhere between 1 and 10 for those countries. So there are 9 countries there because I go and I check it on my frequency, and my frequency is at 9. Go across, I get 9. So there are 9 countries that have more than one, between 1 or 10 billionaires per million people. And then I go here and I say, all right, there is one country here that has between 10 to 100 billionaires per million. So they could have, 40 billionaires per million people. These countries here could have, 5 billionaires per million people. So what's really important is that these are the two you need to add together. You get an answer of 10. One of the most common answers on this was 1, because people looked at it and went, oh, log, I don't really understand it. It's 1's here, so there's a frequency of 1 above it. So I'm going to say, all right, it's 1. Please, please, please do not answer a question like that. Please do not just jump into it and go, I'm really confused by logs. I'm just going to go with it. Try and have a go at this question. If you have that breakdown that I went to, that slide that I went to, you have something like that in your summary book with examples such as this. I know in this question this was less relevant, but having examples like this will make this distinctly easier. So really important you work through that. Now,